Okay, welcome back. It's my pleasure to introduce Franca Hoffmann from Caltech, who will speak about aggregation, diffusion equations, and collective behavior, analysis, numerics, and applications. Please. Oh, no, sorry. This happens when you're not the organizer and you haven't learned by heart the name of the workshop. Sorry, it's Dynamics of Strategic Agents and Algorithms as PDEs.
Thank you very much. And it's a great pleasure to be back here. And I guarantee there will be aggregation diffusion equations in the talk.
With no stress.
No, there will be lots of PDs. Okay, so it's really exciting to talk about this topic here. It's the first time I'm presenting on this. A big part of this is still ongoing work. There's already a little bit online since it got accepted to NeurIPS. This is my first time ever that I submitted something to a machine learning journal. So, you know, it's the usual short format and then very long appendix with PDE analysis results in this case. So this is joint work with Lauren Konga, who's here. Lauren, where are you? Maybe you can wave. Yes. So Lauren is my PhD student at Caltech. And Eric Mazumdar, who's also a colleague at Caltech. He works at the intersection of machine learning and economics. And then Lillian Ratliff, who's at University of Washington. And you can also find everything on arXiv. Okay, so before I show you our nice PDE model, let me tell you a little bit sort of how we got to writing down these equations. So globally speaking, we're interested in understanding the interactions between people and algorithms. Especially in situations where, okay, so you have people interacting with algorithms, and then you also have people interacting with each other. So one such setting is social media, for instance, where you have people posting content, so influencing each other through the content that they post. But then you also have algorithms that suggest content to people, right? So there you have that interaction. And this can lead to things like polarization, which is effects that we would like to understand. Another setting where this becomes relevant is in finance. You may remember the story of GameStop stock, which is a stock where Reddit users communicated on Reddit about buying the stock, and then were able to affect the pricing algorithm of that stock in such a way that the price went absolutely through the roof. So this is a case where, you know, the interactions between people actually had a huge effect on the performance of the algorithm, the pricing algorithm in that case. And then another example is the gig economy. You may all have taken some Ubers and Lyft at some point. So there were some instances where, let's say, a group of Uber drivers that were all arriving at the same airports switched off their apps at the same time so that the pricing algorithm would then think there's no Ubers available, there's no Lyfts available, so the price would go up. And then they all switch on the app at the same time, and therefore they could all benefit from the higher pricing. So these are all examples where sort of people interact with algorithms. And we would like to understand, like, how stable are these behaviors? And then also, how can we model them? How can we understand what is happening there? Okay, so I will be talking about distribution shifts. So distribution shifts is what you can observe as a result of people interacting with algorithms. So here we assume that we have strategic agents that have some objective. So they want to maximize some utility, for instance, or they want to minimize some loss. And that utility or that loss depends on the parameters of that algorithm. And so then they can change their attributes. The attributes of the people is what the algorithm sees and what the algorithm interacts with, right? So the first point is they want to change their attributes according to their objective, the utility or the loss. Then there's also random disturbances to the attributes. Then you have interactions between people, for instance, because of pressures to become more or less similar. And then you also have external forces. And then, as a result, we observe a distribution shifts. And so this is a very natural setting to go to game theory. And there's lots of very nice results in game theory that model these kind of situations. Now, how I got involved into this topic is because it's very interesting, and it turns out a very useful tool to actually lift these often finite dimensional frameworks from game theory up to infinite dimensions, and actually use PDEs to understand what is happening there. And it turns out you get exactly the kind of PDEs that are the topics of this workshop, aggregation-diffusion equations. All right, so modeling distribution shifts is not new. So one of the existing models is mean shift. So this is one of the state-of-the-art performative prediction algorithms. Let me just explain a little bit these two slides. So you have two distributions. You have, let's say you have those agents that have a certain true label, and another population of agents that have another true label. So let's say label 0 and label 1. And then you have an algorithm that is trying to classify. Okay, so the line is the algorithm. So everybody on the one side is classified one way, and everybody on the other side is classified the other way. So now the distributions evolve because the agents, even though they have a true label 0 or 1, would like to be classified maybe in a different way than their true label, right? So that's the underlying dynamics that are driven by this utility and the loss. So what this mean shift algorithm does is it starts with some algorithm parameters, and then it randomly perturbs these parameters, and then observes how the population responds to that change in algorithm parameters, but it only records the mean of how the population changes. And then, based on that, decides how it will update its current state. So this is what's depicted on the left. And then on the right is what you get with our PDE model. And I will tell you the model in a bit, so then this will make more sense. But just to tell you that you see that on the left, so with this mean shift algorithm, the algorithm is actually not changing at all. Like, it just thinks that where it is currently is optimal, whereas on this side, the algorithm is changing. And you see that here, you have sort of a very strong polarization, like you have this split of the population. But the algorithm doesn't see that because it's not looking at the full distribution of the population, it's only looking at the mean information, really. Whereas on this side, the algorithm adapts, and then you see that you reduce this peak on the right-hand side, right? So this is just to say that sort of some of the state-of-the-art methods that are used currently are not able to really detect this kind of polarization that maybe an algorithm would want to respond to. If you want to know more about the mean shift, you can have a look at this paper. Okay, so that's where we sat down and we said, okay, let's try to think about something where we can model a bit more complex behavior of what the agents are doing. And so on the top, you see stochastic differential equations for agents, which looks very similar to equations that you may be familiar with. So the V up there is some functions that the agents want to minimize. So for instance, the U here could be a utility function, which they want to maximize. And then there should also be a kind of penalty for agents to change from their current position. And so that's the raw tilde is sort of a reference measure, and you want to penalize against that reference measure. So for instance, you can take the raw tilde to take simply the initial condition, saying that you want to penalize agents from moving away from your initial states. And you see that this V depends on X. So X are the algorithm parameters, and Z are the attributes of the population. And then, going to the mean field limit, you can describe the evolution of the density of people. So really to look how the distribution evolves. And that turns out to be a Wasserstein-2 gradient flow of an associated energy function. So now we're back to PDE world, and we can use all the techniques from gradient flows and aggregation-diffusion equations to actually study this situation. So the question is this actually useful? Like, are there actually situations in real world interactions with populations and algorithms where this kind of model makes sense. So I just want to give you an example to convince you that this is a reasonable equation to look at. So this is a study of census data in Colombia. And so you see that, so what's happening is that the government is doing a census of the population at regular intervals, and then based on that information, computes a poverty index for each family, and then based on that poverty index, decides who will receive some government aid or not. And you see this red line is basically the threshold for receiving government aid. Okay? And you see that in 1995, the distribution of poverty index in the population looks pretty much Gaussian. And then what happened in 1997 is that the government released how they compute the poverty index scores and also the threshold for giving out government aid. And then the next census, you observe a population shift, right? So this is what we mean by a population shift. So the question is, can we model this kind of evolution? So you can think of this essentially as a classification problem. So what we're plotting there is the total population, right? So now let's assume that each family either should truly receive government aid or should not receive government aid. So basically you have two distributions, and if you sum them up, you get this distribution that you see there. And so the algorithm is trying to figure out how to classify as correctly as possible who should receive government aid and who shouldn't. But of course the people, they would like to get the aid, independent of whether they classify or not, right? So, okay, so I will explain the full PDE model in a minute, but for this example, consider the PDE at the top. So here we assume that the algorithm, so the government doesn't change. So the government fixed their threshold, that's what it is. They compute the way how they assign government aid. So now this is the equation of how the population evolves. I mean, this is an assumption, right? We don't know if this is actually how people evolve, but let's write down this PDE. So the V is the function that the population is minimizing, and the Q is the probability that the classifier assigns a label of qualified to family that has a certain attribute. So the attribute is what is collected from the census data. And then the X is the algorithm parameter, which here is simply the threshold value. So what I plotted here is the P, since the government threshold is roughly 48. And so the fact that we added the linear term at the end there is to say, in general, people prefer to have a lower poverty index in this context of getting aid assigned from the government. Okay, so if you use that model, what you get is this plot. So the lines is the true data that was collected from 1995 and 1998. And then we used 1995 as the initial condition. And we had to decide how to split this full population into people like label 0 and label 1, let's say. And so we just chose something, because anyhow there's an evolution, right? It's just an initial condition. So a Gaussian for the people that should not receive government aid. So their true label would be they don't receive government aid. It would be like at the mean, a Gaussian with the mean above the poverty threshold. And then the people that should receive government aid is basically the full population minus that. Okay, and then we run the PDE. We see what we get. And then plot, the total, and then compare to the real data in 1998. I mean, this is just a very simple model because here the algorithm is not reacting, but just to say that, you can actually reproduce these kind of distribution shifts that you observe. But now, what if the algorithm is also reacting? So this is when it gets interesting. So now, instead of just having a fixed sort of threshold, you have an algorithm that updates its parameters based on what the population is doing. So let's say that the algorithm itself has some loss function, L, that it's trying to minimize, and the loss is computed over the attributes of the whole population. So that's why we're taking minus the gradient of the expectation. And then you have like a PDE for the population as well, evolving the same way as before. And so when Lauren first came and talked to me about this, we said, well, this is an equation for a vector that is coupled to an equation that is a PDE. But actually, you can also lift this equation for the algorithm to measures and actually consider a coupled system of PDEs. So mu now is the distribution of parameters for the algorithm that is evolving in a way that it's minimizing the loss function. And so now you get, well, two coupled PDEs that in principle can be quite complicated. So we consider two different cases that appear in different application settings. One is an aligned objective, where basically the algorithm and the population, they're trying to minimize or maximize the same thing. So this could be in recommender systems, for instance. Like an algorithm wants to recommend you something that you like, and you want to be recommended something that you like, right? So in that sense, your objectives are aligned. And you can actually write this as a joint gradient flow. So you can write down one energy functional for both the rho and the mu, and then you can write down a joint gradient flow resulting in this coupled PDE. I haven't told you yet what the G is, but I will do that in a minute. So that's one setting. And now we can use the theory of gradient flows to study this. And what's very interesting is that, at least for me, this was the first time that I saw this kind of coupled PDE system appear in an economics context. Like, I've seen these kind of equations from what some of you guys are doing in math biology systems, right? If you have multiple species that are interacting. And so it's the type of interaction here is different than what you see in biology. But of course, the mathematical techniques are very similar and can be transported. Now, in a lot of other application settings, you end up having competing objectives, and then you don't have a gradient flow anymore. You can write down a different functional where now, let's say the population is maximizing and the algorithm is minimizing. So now you have a kind of min-max dynamics, and that's a bit harder to analyze. By the way, feel free to stop me and ask questions if in the middle.
So in the last two, there is not a joint gradient flow structure.
This one, no. Yeah, and that's why the...
With respect to some reference.
Yes, and you can, this is very general because you can you can think of what should the dynamics for the rho be, what should the dynamics for the mu be, depending on your application, and then you can, as long as you have this divergence structure, right, of your evolution, you can most likely find such a GC so that you can write it in this way. But because it's not a joint gradient flow, you can't use the usual techniques. And so that's why it's an interesting mathematical problem. And so a lot of these, especially the competing objectives, have been studied quite a lot in game theory, but mostly in finite dimensional settings. So now looking at this coupled PDE system is sort of pushing the boundaries of what's known in game theory. And at the same time, in terms of PDE theory, it's like a new interesting applications where you have different types of interactions that you want to handle. Okay, so now I want to give you some more precise ideas of what kind of functional and like what kind of analysis you can do. So let's first talk about the aligned objectives. So then you have a coupled gradient flow. So you can write it in a joint Wasserstein-2 metric. Okay, let me spend just some time explaining why we wrote down the functional this way. I will say something about F1 and F2 in a second, but just in this formulation, what we're doing is we're fixing, let's say, the population that has true label 1. They don't evolve. And now we're looking at the evolution for the agents that have true label 0. Of course, the next step is to look at the evolution of both of them. And then you have 3 coupled PDEs. But in terms of the strategy and the analysis, that's not too different. So That's where we said, okay, let's fix first of all the guys that have true label 1. And then for the algorithm, since we're not putting any diffusion on the algorithm parameters for now, if you start with an algorithm that's a Dirac, then it will remain a Dirac. So basically, you can think of the mu as being a Dirac at a certain point where the point evolves. And then, so the rho tilde is this fixed reference distribution that I was mentioning before. And then you have this parameter alpha, which is just a constant that tells you how much you're penalized for diverting from it. And then this x0 is also is a fixed algorithm parameter where you penalize deviating too much from it, in this case with the quadratic term. Of course, we chose the function in such a way that it has nice properties and that we can do analysis, right, to start somewhere. But then you can say, okay, how can you relax these kind of expressions? So this is sort of how you can think of this setting if you have like a 1D situation. I hope this is the right version of the slides. Yeah, because I wanted to write recommender systems. So when you have recommender systems, then you're in the setting where you have aligned objectives. And here, this is a 1D. Like, if you want to think of it in the way of the x of t being a threshold, and then you get classified one way or the other if you're above and below, then it's a 1D problem. But all of this, of course, also works if you have any dimension, if the z and the x are even in different spaces, if the mu is not a Dirac but a general measure. So you can really think of this in a very general framework. Okay, so once you fix this energy function, I plug this into the joint gradient flow. This is the equations that you get. And what I haven't told you yet is now what is the F1 and the F2? So the F1 is really the interaction term between the rho and the mu. So it's sort of the cost that, in this case, both the agents and the algorithms have to pay if an agent that has true label 0 puts forward an attribute z, while the algorithm has parameters x. And then the F2 is the same term, but now looking at the agents that have true label 1. But since we're not evolving those agents, you see that in the minimization over rho, that term doesn't even appear, right? So the rho by here does not evolve in time. And then W is an interaction potential between agents. Okay, so we have some nice sort of results on convexity properties and convergence properties and existence of minimizers. And for that, we need some assumptions. So just to say that these assumptions, and also the proof strategy is very similar to the paper by José, Robert McCann, and Cédric Villani, which looks at basically Wasserstein two gradient flows when you have energies that have an external potential, an interaction potential, and then some sort of diffusion. And especially the equation for rho is right in this framework, and you can use similar assumptions. The difference is, of course, that here you have two coupled PDEs, not just one PDE. So you have to sort of check a little bit that everything goes well, but that's where the assumptions come from. So it's all very natural, like you have a lower bounds on the Hessians for the F1 and the F2. Then since you have minus log rho tilde in there, you have basically lower bound on the Hessian of the minus log rho tilde, right? And then you have some convexity assumptions on the interaction potential as well. By the way, if anyone has any ideas of how we can potentially simplify or optimize these assumptions or any of the results, I'm very happy to talk to you. This is a first step since it's something that we're still working on. So here's then what you get in terms of results. So you get existence of steady states and convergence. So for the convergence, you get convergence in energy or in relative energy. So here the GA is with respect to the steady state that exists. And the lambda A is the rate of convergence, which is exactly dependent on your convexity bounds that you get on the functionals in the energy. So that's very natural. Any questions? Okay, so I want to give you some ideas of the proof as well, sort of as a sketch. So this is the aligned objective case. So for the aligned objective case, since we have this joint gradient flow structure, it's very classical in terms of PDE analysis. So we show that the energy is lower semi-continuous, and that is displacement convex with constant lambda A, which of course comes from all the convexity assumptions. And then you can show existence of minimizers using the direct method in the calculus of variations. And then you can prove our three favorite function inequalities. But now for GA, where GA is the energy on the joint space, like product space of the measures rho and mu. And then you just differentiate the energy along solutions to the equation. You can then bound the dissipation using the generalized log-Sobolev inequality, and then you use Grunwald and Tanagant, and then you get your rate. And yeah, use Talleyrand then to get the convergence in the distance. Okay, so this shouldn't be any surprises up to here. Now, the competing objective, this one is more difficult. So now let's say that the population is maximizing the energy and the algorithm is minimizing. And the energy now is different. So of course, the energies that we pick are very specific choices, right? You can choose way more general energies depending on what your application is. But if you look at this energy, GC, so C for competitive, you see that it's exactly the same as the other one, except these two signs. So the last two terms have now switched sign. So why? So if you look at the equation for mu, the equation for mu has actually not changed, because these two terms that switch signs, they don't depend on mu, right? So if you take the first variation in terms of mu, then they just disappear. So it's the same equation. Now if you look at the equation in rho, since we changed the signs, but we are now minimizing instead of maximizing, the terms from the interaction and the KL, they don't change, right? So the only thing that actually changes is the F1. So the F1 term is the interaction between the rho and the mu, and we're now saying that this cost F1, the algorithm is trying to minimize it, whereas the agents are trying to maximize it. So this is the only sort of challenge then here, this F1 term. Okay, and so now that we're in this min-max setting, we're not anymore looking for minimizers, we're looking for Nash equilibria. And so this is the definition of a Nash equilibrium in this context. And so we would like to show existence of such a Nash equilibrium, and then we would like to show convergence to it. Okay. Now to do that, we need some more assumptions than in the aligned objective case. So basically in the aligned objective case, you saw that we had a bunch of assumptions that have lower bounds on the Hessians of the terms involved. And now we need some upper bounds on F1 and F2, the Hessians of F1 and F2, or various types of upper bounds that we collected here. And again, I think probably some of these assumptions can be improved or optimized. For sure, for instance, if you assume more convexity on the interaction potential W, you could relax some of the convexity assumptions of the F1 and the F2 and so on. But this is just to put them there and make sure you can see them. Okay, so these are results that are not yet in the version that is available online. So this is something that we're working on right now. So this is now proving convergence under these additional assumptions to a Nash equilibrium, which we show exists. And the proof strategy here is a little bit different than what we did for the aligned objective case. And I will comment in a second about the proof, the different ingredients. But you see that the rate of convergence now depends, as before, on the lambda 1 and lambda 2 and the beta, but then also this lambda b. And the lambda b now depends on this capital lambda 1, which is the upper bound of the Hessian as well. Okay. So let me mention a few things about the proof. So the trick is to define another energy. So we have this energy GC, and now we define this energy G hat that takes 2 pairs of entries. And that will actually allow us to prove the existence of a Nash equilibrium, but with using just the fixed point theorem for the G hat, essentially. So we do the same strategy showing that GC's displacement convex in mu, and then displacement concave in rho with different parameters. And so then you can conclude that the G head is uniformly displacement convex in lambda c for the first argument, if you fix the second argument. And so now for the existence of a Nash equilibrium, we do this fixed point theorem, sort of a generalized version of the Browder fixed point theorem. And then, there's sort of classical arguments to say, why is this fixed point now? So this fixed point is also automatically a critical point, and it is a Nash equilibrium. But then to say that it's a steady state of the PDE, you still have to show some additional regularity. And then in order to get the convergence, now we're not using the strategy of the function inequalities, but just directly differentiate the Wasserstein distance, or the joint distance, and then use all the assumptions on the functionals to basically explicitly derive a bound that we can then integrate. So after we know that the Nash equilibrium exists. So that's the general cooking recipe. So if you look into the NeurIPS version, or the version that's on arXiv right now, what you see there is actually a timescale separated case. So the argument that we did there for the full, competing objective case is a bit more complicated. And so what we had in the first version is basically to say, okay, either the algorithm reacts infinitely fast to the changes in the population, or the population reacts infinitely fast to the changes in the algorithm. And so then we looked at these 2 cases separately. And I want to just, so you can find all of this in here. Let me just quickly explain the setup. So in the first case, so if you have a fast algorithm, what that means is that given some raw, so given some distribution of agents, I can point. Does it work? Okay. So given some distribution of agents, and assuming that your algorithm is a Dirac at the points, then what is the optimal X bar? Right? So then this is a vector in RD, or whichever space the algorithm parameters live in, and this depends on rho, right? And then you take that and you plug it, back into, nope. Oh, this is forward or backwards? Okay, we're here. So you take this B of rho, which is the best response of the algorithm to the population, and you plug that back into your PDE for the rho, and you just obtain one PDE now, right? But it's a complicated PDE because you have this dependence on the best response inside the energy, right? Which is defined through a minimization problem. On the other hand, if you have fast agents, then what you do instead is, let's say again, you assume that the algorithm parameters are Dirac. So your algorithm parameters evolve according to just an ODE, let's say an RD. But now the rho in there is optimizing, or maximizing in this case, infinitely quickly. So basically, this R of X of t is a probability measure. So that's the best response of the population to the algorithm. And you can think of lots of examples for both of these cases where it makes sense to look at this timescale separation. For instance, in the first case, in online advertising, you can say that a website is able to update its behavior much quickly than maybe us people change the way how we interact with the website. Or the same with Uber and Lyft, like the way how customers maybe adapt their behavior is slower than the company can update what they do in the algorithm. And then you have the other case where, for instance, a population interacts with banks giving loans or governments giving out some benefits or putting out some rules, it takes some time for the government to adjust their regulations and the way how they distribute aid, whereas people are then able to adjust their behavior on a much faster time scale. All right, so that's the two timescale separated settings. And then I won't spend too much time on this because the flavor of this is very similar to the result that you have seen, but essentially we show existence of a maximizer or minimizer in both cases, and then exponential convergence both in energy and also in distance, either the Wasserstein-2 distance or just the Euclidean distance, depending on which case. And I want to just comment a little bit again on the proof strategy because even though it's in flavor a bit similar to the aligned case in the sense that you now only have one equation to deal with, right? Because you can plug the best response into the equation for the other guy, but you have to be a bit careful because you have this very complicated dependence of the best response on either the x or the rho. And so the interesting point there is that, so in game theory, if you do this in finite dimensions, there is Dansken's result, which is basically saying that if you first differentiate the function, so you take the gradient, and then you plug in the best response, is the same as if you first plug in the best response and then you take the gradient. Because if you think about it, okay, sorry, I'm going the wrong way again. Yeah, so this is what we want to use in order to show the concavity, because what we want, or the convexity, depending on which case you're in, you want to show the concavity or the convexity of the full function, like g of b, depending on rho, but then you have the dependence of rho in the first argument, which you know how to deal with because you have your nice convexity assumptions, but then you also have the dependence of rho in the best response. And that's a minimization problem, so that's difficult, right? But if you use Dansken's result, then that actually becomes manageable. Other than that, it's a very similar strategy. There's one additional challenge that we were able to address thanks to discussions with Filippo Sant'Ambrogio, which is that in the case of the fast agents, you also need to show that the best response now of the population is actually continuous in the population. And that's not so simple to show. So you have to do an additional gamma convergence argument in order to get that. And then you can use the same strategy as before. Okay, how am I doing on time? Perfect. Okay, so then let me start wrapping up. So basically the overarching question is how can we model population dynamics under the influence of some algorithm when people interact with algorithms? And so the first question is, does the model describe real-world data? Well, I showed you one example where that's the case. I think there's many more. We were discussing also like situations with loan data applications and so on. So there's definitely more examples that you can think of. Then what are the dynamic features that we observe? So one thing that is interesting, for instance, is polarization, to understand when that happens and how the algorithm and the population react to that. Then the other, so in general, if you're the one designing the algorithm, you're in control of that. So you can now ask the question, how fast should the algorithm learn? So if you think about the different timescale separated cases, is it actually advantageous for the algorithm to react quickly to the population, or is it not? Then, okay, we are assuming here that it's a good idea for the algorithm to do a gradient descent, right? The question is that actually the optimal strategy when you have this kind of complex interactions with a population that also reacts to the algorithm? And then I mentioned this mean shift algorithm that clearly misses out some of the complexities that you observe in the way how populations interact with algorithms. So you definitely need more complicated models to really capture that. And that's what a full PDE model is able to do. But you really want to understand in which settings is that actually needed and what does it give you. Something that we also talked about is what if the algorithm doesn't have access to the full distribution raw? Because in most cases, in real-world settings, the algorithm, when it has to decide how to set the parameters, does not have access to absolutely full information about what the population is doing. So often it only has access to samples. So now how do you do that with a good mathematical formulation if you only have access to samples? And then also something that we have been discussing with a colleague at Caltech, Human Ohadi, who works a lot on kernel methods and Gaussian processes, is how can you now, once you have a model that you trust in, or a model that is complex enough to actually be able to represent the behavior that you expect to see, and now you have data from a specific setting, but you just have data, so you don't know what is the F1, what is the F2, what is the W, you know? Like, okay, we can make some guesses, but it's not gravitational physics, right? It's not physical law, so we can only make guesses. So how can we learn these functions from data? And there's various ways of how you can do that, but kernel methods seem to be a very exciting way to do that. So I think I kind of mentioned everything that's in red here. But if you want to know more details on any of these questions, or what we're currently doing, go and ask Lauren. She's having a poster on that topic tomorrow at the poster session as well. And yeah, I mean, the summary is basically that, well, obviously, in my very biased opinions, PDEs is a very useful tool to try and understand these distribution shifts. And a few things that we're currently working on I already mentioned. So some of the assumptions that we had in the paper that's currently up are a bit restrictive, and we're trying to generalize that. Then also, you know, doing rigorously the non-time scale separated case and having the full analysis for that is something that we're writing up as a journal paper now. Something that I really want to, that I'm very excited about, is the n-player version of what I just mentioned. So now imagine you don't just have one population in one algorithm, but you have several different types of populations, and you have several types of algorithms. And each of them have their own energy functional. And so now you can say, okay, this guy is maximizing, this guy is minimizing, this one only responds to this other population, this one responds only to these algorithms, and you can write all of this in a very general framework. So you can just say n species. Each of them has their own gradient flow, so it's not a joint gradient flow, but each of them has their own energy. And then the question is, what are the assumptions that you need to put on the energy functional so that you can guarantee things like existence of a Nash equilibrium and convergence? That's something that we are writing up right now, and hopefully will be out soon. All right, with that, I will close.
Okay, thank you, Franca, for this very nice talk. Are there questions?
Yeah, thanks. Could you comment more on why the Nash equilibrium is unique in the competitive setting without the time scale separation? Could you comment on why the Nash equilibrium is unique? Does it need some assumption, or?
The assumptions that we have on the energy functions here is very strong. So under those assumptions, you can show uniqueness explicitly. So you can basically assume that you have two different ones, and then you can derive a contradiction. But it's something that you have to prove. So yeah, because here everything is in the end strictly convex or concave. So that's why. But I mean, as I said, like we sort of started with wanting to put all the assumptions that we need so that the analysis is as easy as possible. But now you can say, okay, what if you don't have that, right? What if you have several Nash equilibria? Can you characterize which ones you converge to under which conditions? I mean, those are hard questions, I think. Yeah.
Thanks.
Other questions?
What is if you introduce some delay or something, a memory function in the answer reaction?
That's a very nice idea. There's so many things you could do with this. Yeah, I think that's also what sometimes happens in biology, right? If you have like multiple interacting species, and then, yeah.
More questions? Oh, you're far away.
Yeah, thank you for the nice talk. I have a modeling question. So if I understand well, you assume that all agents are interacting with each other.
Yes.
Is it something which is realistic, or should you consider something with, like we saw in David's talk this morning, with more localized interactions?
I was thinking about that. It's not just in this project, but also in another project that's more biological, where actually taking a cutoff or something that is non-smooth could be more realistic. And then how do you do the analysis? So I was very much interested by that. I mean, at the moment we did, so at the moment we just try to assume everything that makes things easy, right? But I think this is definitely something that you would want. At the moment we're assuming that the W is C2 and that you have a nice control on the Hessian and that, some additional growth conditions also.
More question? No? Okay. Oh, José Antonio.
So how do you see the connection with game theory at the level of the end players? Do you have can you give us an idea?
We basically have a condition. So in game theory, there's a monotonicity condition that people use for these kind of settings. And so the question that we ask ourselves is basically, how can you lift that monotonicity condition to infinite dimensions? And so then there's several ways of how you can do that. And so we were playing around with several versions. But I think now we have a version of the monotonicity condition. So it basically looks at, like you're taking first variations of all your different functionals with respect to the different arguments. And then you want that to be lower, I mean, in average, be lower bounded by a constant times the distance, the joint distance between all of these. And then you want to choose that in such a way that, I mean, this should be a special case, basically, of the n-player game. And when we proved the non-timescale separated case, the explicit condition that we derived just differentiating the Wasserstein distance is basically just a special case of that monotonicity condition in general. If you want, I can show you what we have later.
Okay, so let's thank the speaker again.